Hi everyone, my name is Kai Kiefer. I'm a data scientist. I want to share a project with you that I worked on as part of the Galvanize Data Science Immersive in Denver. It is called DepressionDetect. It is an automated device for predicting depression from acoustics of speech. So a bit of motivation for this project. I like to view kind of depression in three stages: discontent, awareness, and apathy. Discontent I see as this stage where you're feeling blue. You don't necessarily know if maybe you're just going through a down period or it's actually depression. Awareness is the stage where you are acutely aware that you have depression and are willing to seek help. Apathy is the next stage in this process where you know you have depression, but it is too overwhelming or burdensome to seek help. So DepressionDetect is a device kind of aimed at that early and objective detection of depression, trying to catch people in that discontent phase. And I envisioned it ultimately being implemented in kind of a wearable, kind of watch-like device, maybe an Apple Watch or home device like Amazon's Echo. So the question we'll start with is, can you even detect depression from speech? And not semantic content, but acoustics. And the answer is yes, at least from research and academics. People say that there are underlying differences in speech between depressed individuals and non-depressed individuals. So we start looking at some of those acoustic features. We come up with rhythm, stress, and intonation, and we know there's these kind of underlying differences between individuals. And we get more in kind of this space, and we see that the feature space really starts to blow up. So rather than taking maybe a traditional approach and kind of engineering these features of rhythm and stress and running them through a typical classification algorithm, I wanted to pick an algorithm that would kind of latently kind of pick up on all these features that you see. And my answer to that problem was a convolutional neural network. But before we get into that, let's take a look at the data. So I had 50 hours of audio interviews coming from USC. 189 participants went through this process, and on the back end of that interview, they take a psychiatric survey. So I had my audio clips, I had my labels. This was a supervised learning problem, and here was kind of my workflow. So I had two participants, speaker A, and then the virtual interviewer. I was only concerned with the subject, speaker A. So I used a support vector machine to what's called diarize those speakers, to segment them, then perform some kind of feature extraction that I will get to in a moment, and ran it through a classification algorithm. So let's start with feature extraction. So spectrograms are kind of the route I went, and there's many ways to approach this. And I wanted to do a spectrogram because kind of all those latent features that I talked about, and acoustic features rather, in speech like rhythm and stress and intonation, are embedded in this image. So a spectrogram is a frequency time representation of sound. And like I said, embedded in this image, I can't, with the human eye, kind of pick out things like, that's a steep articulation or steep intonation or whatnot. But the hope is that if you pass enough images of depressed individuals and non-depressed individuals to an image classification algorithm, that it can kind of learn the difference between the two. So what is that image classification algorithm? It is a convolutional neural network, or CNN. There are some awesome resources on the bottom, but I will go into a quick overview here. Convolutional neural network kind of passes this filter or kernel over the image. It's made up of many layers. And in early on kind of layers, the network starts to learn things like edges or lines, and in subsequent layers, it kind of puts those edges or lines together and assembles them into what may be a contour representative of intonation or articulation per se. So I pass a bunch of these spectrograms to a convolutional neural network, and sure enough, it starts to learn. This is my specific architecture. I had two convolutional layers with max pooling, followed by two fully connected layers, one with dropout. I won't go in too much here, but here are the results. So when predicting on just 4 seconds of audio, so I pass my network 4-second spectrograms, and I predict on 4-second spectrograms. I had 55% accuracy, so nothing too startling, nothing that's going to replace a doctor's diagnosis, but I then became curious after it started to gain traction. What if we kind of take a majority vote across lots of 4-second samples from a speaker? So that's what I did. I assembled kind of multiple kind of 4-second clips and took a majority vote, just under 3 minutes of audio from each speaker, and with that I got 64% accuracy. So you can start to see it kind of gaining traction. And ultimately, I envision this in kind of a wearable device or a home device, and if it's constantly learning from a user over time, perhaps using kind of a Bayesian approach, and perhaps over the period of weeks or kind of months, that maybe does gain some serious traction and predictive power. So speech data is inherently noisy, and robust kind of models using convolutional neural networks just rely on crazy amounts of data. So I worked with tens of hours of data, but thousands of hours of data are needed at minimum. So I set up this Flask-based website at datastopsdepression.com where you can become a data donor and share a brief audio sample, as well as take the same psychiatric questionnaire that subjects in the original data set took. So everything will be anonymized, so if this is a cause you're passionate about, I encourage you to visit the site. Like I said, my name is Kai Kiefer. This was my tech stack. Thanks for listening in, and I hope you enjoyed and learned something.